Our last section of chapter number 19 is going to be talking about electric power. We'll talk about electric power, we'll talk about energy, and then the last thing we'll kind of do is talk about electric companies and that cost of running electrical appliances. So when we go ahead and we look at the pictures over here on the left-hand side, okay, and specifically right now what I want to do is I want to focus on that top picture. So what you do is you see we've got our battery here and it's lighting up a bulb. Okay, so when we look at our battery, what you'll find out is energy is always going to flow from that high potential end to the low potential. So it leaves the battery at the positive end, travels over to the left, starts going down our circuit, comes over to the right, and we still have high potential. And we're going to have high potential until it gets used by the appliance, okay, or the light bulb. Once it runs through that light bulb, all of a sudden all of that energy or all of that current used by the light bulb, and when it gets used by the light bulb, what it does is it now has low potential. Okay, but because of that electric field, it's still going to push it along until it gets back to the battery at the negative end, and the chemicals inside that battery go ahead and re-energize it to high potential to go ahead and push it back out. What it is if you look at that bottom picture, very similar to what we have here. If you think of water at a high end, or as we think of, say, like Niagara Falls, all of that water up at the top has potential energy. When it starts running down that high potential, it's going down to a lower potential end, and that's really what's going on within the battery. All of that charge, all of that voltage is at its highest potential until it gets used by the light bulb, and then it goes to low potential, continues on until it gets back to that battery to get re-energized. Okay, so again, as we kind of go back over to the PowerPoint now, it says all of that electric potential energy leaves that battery and starts moving through the wire. Once it gets to that light bulb, okay, and I kind of was explaining all of this along the way, that energy is going to get used up. It goes down that waterfall, okay, and falls to that low potential end, okay. So that energy is used up, now is at its low potential. But that current behind, that electric field behind, goes ahead and pushes it back to the battery where it gets re-energized and goes back to high potential. If you look on page 708 of your book, it shows a graph just of this, where you've got it at the high end. All of a sudden it'll fall down and stay down here at that low potential end. But the graph on page 708 actually shows it going back up, so we get back to that high potential end so it can continue moving in that circuit. As we go ahead and we talk about electric power. Electric power, since we're talking about electricity, it's the rate of converting electrical energy. So we're talking about power as being the rate of converting chemical energy to electrical energy, the rate of converting, say, wind energy to electrical energy. So again, it's that rate at which those charge carriers convert electrical potential to non-electrical forms of energy. So we can say that electric power that we're talking about is going to be equal to the voltage being produced multiplied by the current in that circuit. So we can say P equals VI, and when we look at our units, okay, voltage, V, and talking on it on the previous slide, again, sometimes you'll see it called the potential difference. Basically, we're saying if we have a 9-volt battery, it's the potential difference between that high and low voltage, okay, or high and low potential. Current is I, still going to be measured in amperes, and when we have a volt and a current, or voltage and amperes, what you'll end up with power being measured in watts. Now, when we get to the end here, you're going to find out that a watt is a very small unit. We will talk about it being measured in kilowatts, but right now when we use these equations, they will be in watts. We talked about Ohm's Law already, and we said Ohm's Law was voltage is equal to current times resistance. Now we can use that equation for Ohm's Law and actually derive a couple of other equations for power. Now, like I said, V equals IR. Remember, we used to say P equals VI, so if we substitute in the IR where V is, then that's why you get I squared R. So power can be equal to the current squared multiplied by the resistance. Looking at those units, current in amperes, resistance in ohms, and again, it's going to always leave us power in watts. The other one is if we take Ohm's Law and we solve for I, we'll actually get I is equal to V divided by R. So if I put that V divided by R back into that I portion of P equals VI, and we go ahead and simplify it, you'll find out that P is going to be equal to the voltage squared divided by the resistance. Again, looking at units, V is in volts, resistance is in ohms, and again, power will end up being in watts. So if we go ahead and look at a sample problem, it says an electric space heater, it's plugged in, 120 volt outlet. Heater is giving off 3.5 kilowatts of power. And then of course that electric heater, when you think about it, you can see the coils, red electromagnetic radiation, it's also producing the heat. But we're saying 3.5 kilowatts of power. It says calculate the resistance. And you know me, I always like listing all of my stuff. Okay, so because that equation has resistance in it, we have to use the power equation that has resistance in it. So I can go ahead and look at this, and we know that the voltage is 120 volts. Power, okay, I told you power always had to be in watts, so we're going to take that 3.5 kilowatts and convert it to watts, being 3,500 watts, and then we're going to go ahead and solve for the resistance. Okay, so rearranging our equation, R is going to be equal to the voltage squared divided by the resistance. If we plug that in, 120 volts squared divided by 3,500 watts, you'll end up with the resistance being equal to 4.11 ohms. Let's talk about electric energy. So we've got the electric company, okay? What they do is they measure, and they're going to end up charging you a bill, or your family a bill, for how much of the energy your house uses, how much the business consumes, uses. And what you're going to find out is that energy is going to be measured in kilowatt hours, because the thing is, a TV isn't usually on for seconds, it's on for hours. If we're talking about a major appliance, it's going to be operating in kilowatts instead of just watts. Or even a TV that operates in watts, but again, how long we use it and things like that. So again, we want to go ahead and measure it in kilowatts. So they're going to charge you for how much electric energy you end up using. The electric energy that we use depends on the power of the appliance. Different appliances have different power ratings, and also by your unit up here, how long we end up using it. So energy is going to be equal to the power of the appliance multiplied by how long we end up using it. So E equals PT. If we look at our units, power is going to be in kilowatts, time is going to be in hours, to give us that energy in kilowatt hours. A conversion out there that can allow you to go to watt seconds, just the smaller. Also, a watt second is sometimes referred to as a joule, but 1 kilowatt hour is equal to 3.6 times 10 to the 6th watt seconds. This conversion just keeps you from having to take the watts and go to kilowatts, take the seconds and go to hours. If you have something in joules or you have something in watt seconds, you can just do one simple railroad track and use this conversion right here in order to change it over to kilowatt hours, or kilowatt hours being that unit needed. So again, as I said, those electric companies, they're going to charge you a rate. Okay, they're going to charge you money for how much electric energy you use based on this rate. So as you go ahead and you look here, cost, what it's going to charge your business or what they're going to charge your family, is going to be that energy used multiplied by that rate. So again, we can say cost, energy multiplied by the rate. Energy has to be in kilowatt hours. Rate, it's a money thing. It's a money charged per unit of energy used. So dollar amount per kilowatt hour, and then of course cost going to be measured in dollars. In Nebraska, just letting you know, it's a little less than 10 cents per kilowatt hour, so that average cost is about 0.096 cents per kilowatt hour. So let's look at an example problem, and I'm going to have you actually do a couple of equations here, one where you're going to calculate energy, and then we're going to continue it on to calculate how much money ends up being spent. So it says, how much does it cost to operate a 100-watt light bulb 24 hours? So we're just going to run it one whole day, or maybe you're operating it 24 days at 1 hour apiece. If the rate for electricity is 0.08, so a little bit less than Nebraska, but 0.08 cents per kilowatt hour, 8 cents per kilowatt hour. So the thing is, we know that we have to end up calculating that energy. Okay, and to calculate energy, we said that was going to be equal to power times time. Now remember, I said power had to end up being in kilowatts. So 100 watts is going to be equal to 0.1 kilowatts. And as it says there, time, it is in hours already, so time 24 hours. So first thing we're going to do is calculate that energy by taking the energy to be equal to power times time. So energy, that 0.1 kilowatts multiplied by 24 hours. So you're going to find out that for 24 hours to operate a light bulb, 100-watt light bulb, about 2.4 kilowatt hours. The rate we said was 8 cents. So cost is going to be equal to the energy that we calculated up here, okay, multiplied by rate. So cost, again, that 2.4 kilowatt hours multiplied by 8 cents, you're going to find out that it's going to cost the family or the business about 19 cents to operate that one light bulb for 24 hours.